Okay. All right, we are now recording. Okay, so I have a bunch of slides, and my concern is that I have too many slides. But since that proved to be helpful last week, I'll do the slides. And if it turns out that I run out of time, I have a set of problems here that I can post, with solutions, even if we don't get to it. So let me go through and connect. Here we go. Okay, so everybody see the presentation, I hope? It says electric charge and electric field.
Yep.
And once again, Kelly, if I may deputize you, let me know if there are questions that pop up in the chat, since I don't see them when I'm in presentation mode.
Yep, no problem.
All right, so let's talk about this. The material today is, I guess, chapter 16, electric charge and electric field. So the material in the world has a property that we call charge. There are two kinds of it. One is called positive and one is called negative. The assignment of positive and negative, by the way, comes from Benjamin Franklin. And in a certain sense, he got it wrong, as you'll see a little bit later, perhaps. Some things would have been a little bit nicer if he had reversed what he called positive and negative, but ultimately it doesn't really matter. But it would have been a little bit nicer if he'd done it the other way around. But okay. The thing about charges is that they push on each other. Like charges repel each other. Opposite charges attract each other. I think you all know this already. I'm just reviewing it. Charge is not continuous. It comes in discrete quantities. So, for example, electrons and protons are sort of fundamental charge units. These carry the smallest fundamental amount of charge. If you want to talk about quarks, then maybe not. Quarks, which don't exist by themselves, can be thought of as having 1/3 of a charge. But as I said, they don't exist by themselves. And quarks, by the way, are subunits of protons, but not subunits of electrons. Electrons are basically just electrons. They don't, as far as we know, they're not made of anything else. And they just have a unit charge. All right, an amount of charge is measured in coulombs. That's the unit that you measure amount of charge in, named after a French guy, Mr. Coulomb. And the charge of one electron, since Mr. Coulomb did his work well before we knew about electrons, the charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. The charge of a proton is the same number, but positive. Okay, a couple of interesting factoids that I found on Wikipedia. So with the caveat that it comes from Wikipedia. Charges in static electricity from rubbing materials together are typically just microcoulombs. And the amount of charge that goes through a lightning bolt is like 15 coulombs, although it can go up to 300, 350 coulombs. And remember, that's amount of charge. The thing about the lightning bolt is that all this charge, the 15 coulombs or the 100 coulombs or how much it is, travels very, very, very quickly through a humongous voltage. We'll talk about voltage later in the semester. So it's interesting to compare the amount of charge that goes through a typical AA battery from being fully charged to discharge. It's 5,000 coulombs. The thing is, it's a little bit of a trickle. It's compared to the lightning bolt, it's just a trickle of movement of charge, but it goes on for a very long time, so you get a whole lot of it. Okay, so later on in the semester, we'll talk about voltage, as I said. Lightning bolts have huge voltages of several 100,000 volts, and AA battery is just 1.5 volts. And we'll talk about current, and current is the number of coulombs passing by a point in a certain amount of time. So the faster the charge moves, the more current you have. The more current, the more charge that passes by, the more current you have. But that's later. Let's go and discuss the Coulomb force. So as I said, two charges will exert a force on each other. They repel or they push each other together, pull each other together. Let's say that there are two charges, little q and big Q. Those are the number of coulombs. There's a force that they exert on each other. Here's one charge and there's the other. They're separated by a distance r. The force has this magnitude. And I don't know why books don't present it this way. Notice that I put the absolute value signs so that on the right side, it doesn't matter whether I have a positive or negative charge. I'm taking the absolute value. And that'll give me the magnitude of the charge. So Q and Q are the number of coulombs. R is the distance between them. K is a specific number. It's approximately 9 times 10 to the 9 Newton meter squared per coulomb squared. Voice is a little heavy today.
I have a question.
Go ahead.
So the magnitude of it, you're taking the absolute value, that is different than whether they're going to attract or repel and what the overall force is?
In a moment, I'll tell you the direction of the force, and it'll be that exactly.
Okay.
So force is a vector. It has a magnitude and a direction. This is the magnitude.
Okay.
Notice, by the way, that it looks just like gravity, right? Remember, force of gravity was big G, which was a particular number with these units, except for kilograms and coulombs. Big G, and then mass 1, mass 2 divided by r squared. So it looks a whole lot like gravity. The difference is that mass is only positive, and we get positive and negative charges. But okay, so there's the formula for the magnitude of the force. The direction of the force comes from the rule that we mentioned before. So if you have like charges, they will repel, and opposite charges will attract. So here are two opposite charges. One is negative 7.7 microcoulombs. The other is positive 7.4 microcoulombs. What are the directions of the force? Well, they are opposite charges, so they attract each other. The force that this exerts on this one is to the right. The force that this one exerts on this one, wait a minute, I said the other way around. The force that this one exerts on this one, which is this force, is to the left. Like charges repel. Here are two negative charges. They push each other apart. Positive charges also repel. They push each other. Wait, my hours are wrong. They should push each other. They should push each other apart. Sorry about that. I'm going to fix that now so that I don't screw things up. There. Okay, so those are the rules. There's also the principle of superposition. Again, I don't know why the books don't make a bigger deal of this. If there are more than two charges in the universe, then to find the net force on one of them, find the force that every other charge exerts on it individually, and add these forces as vectors. Those forces are vectors. Remember, the force is a vector. So for example, let's suppose that the universe consists only of these charges here. There's 1, 2, 3, 4, 5 of them. These 4 are negative, and this one is positive. Suppose that they are fixed in space, and we would like to know what the force on this one in the middle is. Wait, let me get my pointer out. See what I'm doing? There. We would like to know what the force on this one is. So the procedure is you consider just one of the other charges, ignoring all the others, and figure out the force. So for example, the force due to this one on this charge is upwards because they repel each other. And suppose it has that magnitude. It's attracted to this one, so there's a force in that direction due to this one. And the other charges give you these forces. This one comes from that one, this one comes from that one. So these are the 4 forces that act on this charge. To find the net force, we add them as vectors. So you could do it geometrically. Here I have arranged, I just copy over that vector there, and this one, and that one, and that one. And the sum of these vectors is from the tail of the first one to the tip of the last one, that green arrow there. So the net force on that middle one is this. So that's an illustration of this principle of superposition. Later we'll do an example where we algebraically calculate what the net force is. In fact, we'll do it right now. So here's a one-dimensional example. Suppose that there are these 3 charges all in a row. They're separated by the same distance, 0.35 meters. Here are the charges, positive, positive, and negative. Let's find the net force on the leftmost charge, this positive 65 microcoulombs. What's the force on this one? you consider the other charges one by one. So F1 will be the charge due to this one, excuse me, the force due to this one that acts on our charge of interest, F1. And here's the magnitude of F1. So the magic number, 65 coulombs here, or microcoulombs, excuse me. So the micro is the 10 to the minus 6. And the charge of this one is 48 microcoulombs. And then they're separated by a distance of 0.35 meters. And so you square that in the formula. Calculate that, and you get 228.92 newtons. So we know the magnitude of this force. The direction is as shown because we know that that's positive, so they will repel each other, meaning that this one will exert a force on this one to the left. All right, so we did that by ignoring the existence of this one. Now we will pay attention to this one, ignore the existence of this one, and figure out the force that this one exerts on the leftmost one. Its magnitude is given here. So the magic number, the 65 microcoulombs, which are here, and 95 microcoulombs. Notice that this is a negative charge, but I ignored it because of the absolute value sign that I'm using. And then in the denominator, I have the distance between the charges, which is 0.35 twice. So 0.7 meters. And then you square it. That gives me a magnitude of a force, 113.27 newtons. And notice its direction is to the right because it's opposite charge. But this one on the far right is negative. The one that we're interested in here is positive, so they attract each other. So the force that that one exerts on this one is to the right. Okay, so we're finding the net force on the leftmost charge. The other two charges exert these forces. You can see they're in opposite directions. Now we have to add these things as vectors. Since we're only in one dimension, that's easy. What we have to do is put a coordinate system on it in order to decide which way is the positive direction. Notice that I'm indicating that to the right is my choice of where the positive direction is. So that means that F2 will be positive and F1 will be negative. We know its magnitude, and just by choice of coordinate system, I decide whether these numbers are going to be positive or negative. F1 is negative because it points in the negative direction. F2 is positive because it points in the positive direction. To get the net force, add these numbers. And you get negative 115.65 newtons. So I'm taking negative 228.92 newtons and adding 113.27. That's my result. The overall result is negative, meaning that the net force points to the left. And it has magnitude 115.65 newtons. Okay? Is there any question about what I did in this example?
Not so far. It makes sense.
Okay. Very important to keep in mind the magnitudes of the forces and the directions of the forces. And then when you go to figure out the net force, you add the forces together as vectors. You have to take into account the directions and use a coordinate system to do that. All right, so that was an example in one dimension. Let's do an example in 2 dimensions. So here we have an equilateral triangle. Notice that the distance between the 3 charges is the same, 15 centimeters. And the charges are all the same. They're all positive 17 microcoulombs. Find the magnitude of the net charge in the bottom left charge, the one over here. Okay, so again, we do the superposition principle. Here is the force that this bottom right charge exerts on the charge of interest. Since they're same charges, they repel each other, so it pushes to the left. I'm going to call that F1. And I've ignored the presence of this one in figuring that out. Now I'm going to ignore this one that I was paying attention to and pay attention to the one at the top. It exerts a force F2 on this charge down here. Now because these distances are the same and the charges are the same, the magnitudes of F1 and F2 are the same. They just point in different directions. That's just the way the problem is set up. the magnitudes turn out to be the same, but you see the directions are not the same. So now to figure out the net force, we have to take these two vectors and add them, respecting the fact that they are vectors. I hope you remember this kind of manipulation from last semester. Okay, so let's do that. Actually, let's not do that. Let's first figure out what the magnitudes of these forces are. So I just plug it into the Coulomb formula. Everything's positive, so I don't have to worry about the absolute value signs. In both cases, it's 17 coulombs and 17 coulombs. In both cases, the charges are separated by 15 centimeters or 0.15 meters. There's that square there. There's the magic number. That works out to be 115.45 newtons. Those are the magnitudes of the two forces. They're the same. All right. So now, in order to add these as vectors, we need a coordinate system. And since we're in 2 dimensions, I need an x and a y. So positive x is to the right. Positive y is upwards on the screen. Now let's express each one of these vectors in terms of this coordinate system. Pay attention to F1 first. We'd like to know the x and the y components of it. So hopefully it's obvious by just looking at the picture that there is no y component. Right? It points entirely in the negative x direction. So the x component will be negative, the y component will be 0. So we get this. The magnitude we already figured out. Put a negative sign to get the x component, that points in negative x direction, and no y component. Okay? I've expressed F1 in terms of the coordinate system that I drew. Make sense? Feel free to interrupt me if you have a question.
No, we're good so far.
Very good. Oh, there's something. Was that a question?
No, Julia just said yes, as in like we're clear.
Okay, thank you. Let's now consider the other force, F2, and express it in terms of the xy coordinate system that I drew. What are the x and y components of that? So clearly we're going to need this angle. We know that this is 60 degrees because it's an equilateral triangle. And we know that that's 60 degrees because we have two lines intersecting, and so opposite angles are congruent. And now I'm going to copy that vector down a lower. I've done a little magnification here, so it's a little easier to see. I copied this vector here just for reference, magnified. This is the x component that I want to figure out. That's the y component I want to figure out. That's the 60 degrees. I hope everybody remembers the trigonometry, in particular the triangle. Those of you who were in my class last semester, I made a big deal about this triangle. You should have printed it out and put it on your bathroom mirror and looked at it every day, right?
Still there.
Right? It's still there. All right. Okay, so I won't belabor that right now. I'll point out that if I want this side of this right triangle, I will use the cosine. So that the length of this side of the triangle is the hypotenuse, 115.45 newtons, cosine, because of the adjacent side, 60 degrees. And if I consider this right triangle here, I want the side over here. Actually, no, consider the same triangle. I want the opposite side. That would be this one, which is the same as this. That involves the sine. Okay, so this tells us the lengths of these blue arrows. And in reference to this coordinate system, where to the right is positive and up is positive, I would say that the x components of F2 is negative, this value here, and the y component is also negative. So, and calculating out what that is, we get these particular numbers. Okay, so I did a little trigonometry to figure out the x and y components. I noticed that those components point in the negative x and negative y directions. So here it is. I have the x and y components of both vectors. Now I'm in a good position to add them together as vectors. To get the x component of the sum, I add the x components of the two vectors. This. Here's the x component of 1. Here's the x component of 2. Add them together, and I get negative 173.1575 newtons. And for the y component of the sum, I add the y components of the vectors. I'm just adding 0 to this number here. End result is here are the x and the y components of the net force, which therefore tells us that the net force is like this green arrow here. Okay. Again, feel free to interrupt me if you have a question. Hearing none, I'll continue.
We're all good.
I now know the x and y components of the net force. And now using the Pythagorean theorem, this is a right triangle, right? This side is the same as this side. I can get the magnitude of the net force. Works out to be about 200 newtons. And that was the question. Find the magnitude of the net force on the bottom left charge. If we wanted to, we could figure out the direction of the force by, say, calculating this angle here. But I bet you know what the angle is just by symmetry.
60.
No. If I were to extend this angle all the way back, it would go right through the middle of this triangle, right? So this is 30 degrees here. If I do a dotted line all the way back here, it would go right through the middle of the triangle. So I'd have a 30-degree angle over here. Yeah, a 30-degree angle here and a 30-degree angle there. Or you could do the trigonometry. Okay, I go on in the interest of time. Let's talk about the electric field a little bit. So the electric field. Let's first review. If you have a charge here, Q1, that's fixed in space, let's say it's a positive charge, and I put another charge Q2 over there will be a force. There's the Coulomb force, and the force has this magnitude. The direction in this case is repulsion because they're two the same types of charge, positive charges. If you think about it, it's kind of spooky. It's like gravity. Gravity is kind of spooky. Physics is not going to tell you why this force is there. Physics is going to tell you the force is there. The force has this magnitude and has this direction. It's not going to tell you why. Right? It's a very fundamental feature of the universe. There are forces. In fact, we've identified 4 kinds of forces. One is gravity. One is this electric force, which in more generality turns out to be an electromagnetic force. And then there are 2 more forces that are important at the atomic level. There's something called the strong force and the weak force. Those are rather complicated. So I won't say very much more about it right now. But we just basically say here, these forces exist. They behave this way. We can't tell you why. Except in the case of gravity, we have a little bit different explanation. But, all right. The concept of an electric field comes about by saying, okay, so that force is there. It's kind of spooky, but let's break it into 2 parts, just conceptually. So the first part is put a charge somewhere. Assume that there's nothing else in the universe except that this charge here. By virtue of the fact that the charge is there, an electric field is set up everywhere in the universe. The electric field is given by these vectors. So every point in space has associated with it a vector, which is the electric field at that location, and it comes about due to the presence of this charge. Notice that the closer you are to the charge, the larger the magnitude is. Notice that in this case, the direction of the vectors is outward away from that charge. And so that's the electric field. What are the consequences of the electric field? Well, here's charge Q1 fixed in space. Let's pay attention to this particular point in space. There's an electric field vector associated with it, and that I've drawn it here. Actually, there's an electric field associated with every point in space, but I'm just paying attention to this particular one. And that's the electric field vector for that point. If we put if we put a charge Q2 at that location, at this location right here, then the force will be there. So you see how I broke it up into 2 pieces. The first part is There's one charge. It creates an electric field everywhere in space, and in particular at this point. Then, if I put another charge at that location, the force will be there, and it will have that magnitude. And so that we're imagining this two-step process. Now let's do this. Here is the magnitude of that force. Let's pull out the Q2. Right? What's in parentheses doesn't depend on the presence of Q2. So that's why we call that the electric field. So I'm making this equivalence here. See this three-pronged equal sign? And so what's in parentheses here is the same as the E. So the magnitude of the electric field is then given by this.
So is Q2 directly on top of Q1?
No, Q2 is here and Q1 is way over here.
So they're just like it.
See how they're far away? In fact, they're a distance r away from each other.
Okay.
Now, we put Q1 here and fixed it, and then paid attention to a location a distance r away.
Okay. Gotcha.
At that location, there's an electric field. It has this magnitude, and that's true. It's there, and that's its magnitude, regardless of whether Q2 is there or not. But when we put Q2 there, it will sense the presence of the electric field, and as a result, experience this force. Okay, so this formula down here at the bottom is the magnitude of the electric field at a point a distance r away from an isolated point charge Q1. And that's Q1 in the numerator here.
So the electric field
go ahead.
change. The electric field will change only when the distance changes, because it's all based on Q1. And
and it can also change depending on the charge of Q1.
Okay.
Here I'm assuming that it's positive.
Okay.
And that comes up in the next point that I'm going to make, which is maybe a little confusing at first, but then becomes a little easier. The direction of the electric field, the blue vector, which is underneath here, the direction of the electric field is the same as the direction of the force that would be felt by a positive chest charge if you put it there. That's why I started with positive charges here. So there's Q1 here, and I put a positive charge Q2 here. It feels the force away from the first one because they're the same charges. So they were repelled. Mm-hmm. Therefore, according to this rule, the direction of the electric field is away from Q1. Okay?
Yeah, I have a quick question regarding the letter Q. It doesn't matter if it's capital or lowercase, right?
Of course not.
Okay, I just want to make sure.
You could all X if you wanted to. What you'll find is that almost every physics book uses Q for charge, and you'll see lowercase and uppercase. In fact, I'll use lowercase.
That's sort of where it gets confusing, is that sometimes they use a lowercase in one instance and then an uppercase in another. And it's sort of...
Yeah, make an effort not to be confused by the symbol itself. Pay attention to where the symbol shows up in formulas, and then you'll assign a meaning to it rather than to the symbol.
Okay, thank you.
Was there another question? I just heard a ding.
No, that was actually, that question I just asked was from lecture that had been asked, and so I just remembered it and wanted to ask. So.
But I hear some dings. Are other people asking questions?
They're agreeing with the question I asked.
Oh, okay. Okay, very good. All right, here's my summary slide of what you need to know about electric field. Here's Q1 somewhere in space. It's positive here. It could be whatever. It could be positive or negative. That would be a positive Q1 or a negative Q1. At some location elsewhere, like this one, there's an electric field. If you put Q2 there, it feels a force. And this is the equation. The magnitude of the force equals Q2 times the electric field. Notice that there are no absolute value signs here. So we are related, but we are relating the vectors. If Q2 is positive, then the force is in the same direction as the electric field. If Q2 is negative, then the force is in the opposite direction.
So would you say that if it's positive, it's repelling, and if it's negative, it's attracting?
Well, it depends on what the sign of Q1 is.
Okay.
As you'll see.
Okay.
Here is the magnitude of the electric field. I put positive absolute value signs, so you don't have to worry about positive or negatives. Magnitudes are always positive. And once again, the direction of the electric field is the same as the direction of the force that would be felt by a positive test charge. So Q1 here is positive. When I put the positive test charge here, it's repelled. That's why the force points to away from Q1. If Q1 were negative, and I put a positive test charge at this location, it would be attracted, so the force would be down here, and the electric field would point to the lower left. And I should have had the drawing of that. I thought I did. Okay, does that make sense?
Yes, it does.
Units of the electric field, they follow from that equation. We have newtons per coulomb. Electric field is measured in newtons per coulomb.
Can I ask a question about coulombs?
Go ahead.
Oh, wait. Okay. No, is it, so it's just a C, but like newtons where it's like kilograms per meters, right?
No, coulomb is coulomb.
It's just a coulomb.
In the same sense that mass is in kilograms,
Okay.
charge is in coulombs.
Okay.
So a fundamental unit. So that formula tells us that the electric field is newtons per coulomb. Let's make sure that it's consistent with this formula. So the K has these units, newtons meter squared per coulomb squared. You'll remember that from the Coulomb formula. This Q is in coulombs, and that distance squared is in meters squared. And so you see that you cancel out the meters, and you cancel out one of the coulombs, and you're left with newtons per coulomb. So it's all consistent. I recommend always checking your units. If you find an error in your units, you did something wrong. All right, notice this. At this location in space, if the electric field points to the right, and I put a positive test charge at that location, it will feel a force in the same direction as the electric field. It just follows from this equation. If Q is positive, then F and E point in the same direction. Suppose at this location in space, you have the same electric field. I separated this, right? So this is a different situation. We have the same electric field, but I put a negative charge there. It will feel a force to the left. Negative charge experiences a force this way, opposite the direction of the electric field at that location. Follows from this equation. If Q is negative, then force and E point in opposite directions. Okay. It is too hard to draw arrows everywhere in space. It just gets to be a really messy figure. And so instead of drawing the electric field everywhere in space, instead what we do is we draw electric field lines. And sometimes this confuses people, so stick with me here. Field lines tell you the direction of the electric field, but the electric field is tangent to the field lines. I'll show you an example just momentarily. At any point, the direction of the electric field and the field lines is given by the direction of the force that a positive test charge would feel. So here's an example. Suppose that we have an isolated positive point charge, nothing else in the universe. Here are drawings of the electric field lines. What that means is that, first of all, notice that they point outward. They have these little arrows, so the electric field lines point outward. They do that because if I were to put a positive point charge here, it would be repelled away from the actual point charge. And so that's why these electric field lines point away. Now, if I want to know what the electric field is at this point, then I draw a vector for the electric field, which is tangent to the electric field line. These are straight lines, so tangent is just in the same direction. So that's not particularly interesting. You'll see in the next example something a little more complicated, and then two examples. Okay, so around an isolated point charge, the electric field lines just point radially outward. Around an isolated negative point charge, they point inward. Why is that? Because at any location, if I were to put a positive charge there, it would be attracted to this one. That's why the lines point inwards. And if I want to know what the electric field is at this location, I draw an arrow that is tangent to these lines. And that's not so interesting in the case of straight lines because they just go in the same direction.
When they do the field charge or the arrow direction, they're only basing it on what would be if you put something opposite.
No, not opposite, positive specifically.
Oh, okay. So everything.
Wherever, if you want to know the direction of electric field or the direction of the electric field line, imagine the force experienced by a positive imaginary test charge located there.
Okay, which was your second point. Okay.
All right, so the more interesting example is if there are two charges. What if there are two charges together? Use the principle of superposition. So it turns out you get a figure like this. These curly things are the electric field lines. And the electric field at point P is a vector which is tangent to it. You see how it's tangent to it? Now you might say, well, why is it pointing in that direction? Well, it's repelled by this positive and it's attracted to this negative if I were to put a positive test charge there. Or more specifically, if I wanted to draw, do the superposition principle, if I were to ignore the negative charge and figure out what the electric field were at point P due to this positive charge, it would be in that direction. And then if I ignored the positive charge and I wanted to figure out the electric field due to the negative charge at point P, it would be this. And then superposition tells us just add those two things to get the net electric field at that location. So you see how this vector, actually they're too long. I'll make that correction now. This should look like this. There we go. That's a little more accurate. Okay. No, that's not good. I don't want these lines here. There. See what I do. Here we go. So if I take this vector and I move it over here so that it points this way, actually it's still not right. Okay, I will correct the geometric features of this, but the directions of these electric fields capture it correctly. In fact, okay, let's do it. I do have a little bit of time so that you see what I mean. If I were to add these things as vectors, they would have to look like this. I think they had it right to begin with. So that, I think I did have it right to begin with. Sorry about that. Why am I confused? Okay, there we go. Okay, any question at this point? I hope I didn't confuse you with my little
No,
redrawing.
You made it more clear.
Okay, good. I'm glad. Yeah, so you see how you get. Go ahead, Kelly.
There's one question. Why does the positive vector seem to be slanted instead of straight up? It's because it's
this one here.
Oh, it's because of the positive charge in the center. It's directly away from the pink plus sign. It's directly away from that.
Yeah, exactly, Kelly. Thank you. This electric field vector here is the electric field at location P due only to the positive charge. Remember, I'm using the principle of superposition. I'm ignoring the existence of the negative charge, and I'm only paying attention to the positive charge. So the electric field at location is away from it. That would be like this situation. That one. So if there's only a positive charge, the electric field is directly away from it. For the other one, points directly towards the negative charge because that's the electric field of that location, ignoring the positive charge and only pay attention to the negative one. And then I take these two blue vectors and add them together to get the net electric field due to the presence of both charges at location P. Does that answer the question that was in the chat?
Yes, thank you.
Okay, good. And again, notice that the electric field is tangent to P. So if I wanted to know what the electric field here was, I look at the direction of the line, and then I draw an arrow that's tangent to it. Or over here, it would be straight down, you see. Right? At this location here, let's draw it since I can. So at this location, the electric field is straight down. That location there. The reason why is because that arrow is tangent to this electric field line. And the electric field line has this arrow that points, it's flowing in this direction. Okay. If you have two positive charges, look at what the electric field lines do. They kind of push away from each other, as you see. And if you have a opposite charges, but one of them is stronger than the other, you kind of have sort of a higher density of electric field lines over here than over there. So this is another point which is sometimes not explained well. Electric field lines are everywhere in space, but they're kind of denser where the electric field would be stronger. And so we kind of draw more of them closer together where the electric field would be stronger than out here. But that's a little bit of a trick because the electric field lines really are everywhere. It's just that the electric field is stronger over there and weaker over here. Okay, so we have 7 minutes left or so. I have a problem for you guys to consider. So please have a look at this problem here. And I'm going to have to step out of presentation mode for a second here. How am I going to do this?
You could split your screen if you're looking to take attendance at the same time.
I don't know how to split my screen. That's true.
Just minimize your PowerPoint. Like
while I'm sharing it?
Yeah, just make it smaller. You can still see the drawing, right?
All right. I'm going to try that in a second, but right now I'm going to take a quick screenshot of what's there. I think that would be a way of having a backup. Okay, I now have screenshots of everybody who's here. Now I can go back and share the screen again. Yeah, feel free to take a picture of it if you wish. And what happened to it? Here it is. No, there it is. Okay, Kelly, I'm going to try what you did after. I'll give you guys a chance to work on this. Okay, so consider this fixed arrangement of charges on a square of side length d. Assume that nothing else in the universe exists. What is the direction of the net force on this charge? This one up here in the upper left. So I'm asking for the direction of the force on that charge. Think about that for a second. Okay, shall we review it quickly? Everybody ready?
Yes.
So we're going to do principal superposition. I conveniently moved the Q out of the way. So here is the formula for the magnitude of the force. And here's the principle of superposition. We're going to use basically just principle of superposition. I'm not going to calculate numerically these magnitudeless forces, but I have this problem written up, and I'll post that, where I calculate the magnitudes. Given some numbers here. The force due to the lower right charge on the upper left charge, ignoring the other charges, is in that direction. So because it's attracted, right? This is negative charge in the lower right, and this one is positive charge, so they attract each other. So the force on that one is down and to the left, down to the right, excuse me. The denominator, the distance between them, is the diagonal of the square. So that's what the R12 is when I calculate this magnitude force. And the charges would be Q and Q. Okay, here is upwards is the force on the upper left charge due to this one down here. Now I drew it, first of all, away, so upwards, because this is positive and that's positive, so they repel each other. But I also drew it longer. It has a bigger magnitude. It has a bigger magnitude for two reasons. First of all, there's more charge. Right? This is a 2Q, and that's a Q, as compared to this force here, which just involves Q and Q. But it's also longer because the distance, the R12, when calculating F2, is just D. Whereas when calculating F1, it was the diagonal, which is longer than D. Square root of 2 factor. So since this is shorter, that gives me then a larger force. Right? So F2 is then longer than F1, has a bigger magnitude than F1. And then finally, the force due to the upper right charge points to the left because, again, they repel each other, and it has the same magnitude as F2 because the distance is the same and charges are the same. Okay, so to get the net force on that upper left charge, I make these arrows, these vectors, and add them together as vectors. But you can see by the symmetry that the net result is going to be along a diagonal, but the same direction as the diagonal, just by symmetry. So here I draw that diagonal. So since I know that the net force will be along this green dotted line, let's figure out in which direction it would be. I've got F1 that's already along that diagonal, so that's fine. I figure out what the component of F2 is along that diagonal. And I would need to do a little trigonometry, perhaps. I have to figure out what that angle is. And I know what that is because it's 45 degrees. Right? This is 90 degrees. Diagonal splits it. That's 45 degrees. This is 45 degrees. So the component, this blue arrow, has a magnitude F2 cosine of 42 degrees, 45 degrees. And then I would take the component of F3 in the direction of the dotted green line, which once again would be F3 cosine of 45 degrees. This is 45 degrees by the same argument. All right, so now I've figured out all the components in the direction along the green line. And I've got two sizable components to the upper left and one smaller component to the lower right. So the upper left is going to win. The net force is going to be that way. Now you might say, what about the components in a direction perpendicular to the dotted green lines? Well, you can see that this force has no component in the direction perpendicular to the green line. This one does have a component in that direction. It would point that way. So does this one, except that it would point the opposite way. So those would cancel each other out. So there is no component, just by symmetry, there's no component of the net force perpendicular to the green line. The net force is entirely in the green line. Is there any question about that? I hope you guys remember how to add vectors together.
No question.
I didn't have to use a coordinate system. I just picked this line. and figured out the components. Go ahead, Kelly. What did you say?
No questions so far. Somebody just said goodbye. They have a class. What should I do also?
Okay. Okay. So I will post a worked out solution to this and a handful of other problems, which I didn't get to do. I'm out of time. So that's it. I hope you have a good afternoon.
Very, very helpful. Thank you.
Yeah, I do hope it was helpful. Thank you. See you guys.
Thank you, Dr. Barreto. I just had one question on that last problem you were showing us.
Yeah.
I was wondering why you chose the green diagonal line as like your reference. Or were you saying that we could have chosen another line and somehow when we added the vectors we still would have been able
No, it has to be that line specifically.
Okay.
Are you seeing the picture?
Yes, I can see it. Mm-hmm.
You can see it right now on the screen? Okay, so that confused me a little. So I figured this out, right? And this by symmetry, if I just think about the symmetry of the situation, I know that the net result of this force will be along that diagonal. This one is entirely on the diagonal. This one has 45 degrees here and 45 degrees here. So the components will work out to be only in that direction. Does it make sense when I say that? I'm not sure how else to say it.
No, I think it does. I just needed to clarify it. Thank you, Dr.
Okay.
Barreto. There's also a question in the chat. Someone was asking if you could post any on-paper solutions like you did during your class if you have the time.
I am posting written solutions. Are you asking for the recorded on-paper solutions? I don't know if Kirsten is still here or not.
I am still here. Honestly,
Hello.
either are helpful. I did like the recordings, but if you don't have time, I understand.
I'll see what I can do for you.
Thank you.
I'll certainly will be posting, the written out solution without the video.
Okay, perfect. Thank you.
Okay, no problem.
Bye.
Alex just asked, I lost the connection. What is the direction of the force? Do you see the screen? Okay, I don't know what you just said. Okay, so you see the screen. All right, so let me fast forward to so there it is. So the end result is the net force is up and to the left along the diagonal direction. Okay, you're welcome. Okay, so I'm going to now, okay, you're welcome. See you guys. I'm going to stop the recording. And I'm going to now go to my next class. So